Our DLD project is called Catching the Rain. Now let's first see the simulation of how the circuit works. So, as you saw in our circuit, we are actually playing the game whenever the LED lit up at the same time at the last column of the dot matrix lit up, we counted a win, and first challenge was to disable the 8 rows of the dot matrix display. As the rows of the dot matrix display lit one by one, and after reaching this row, it would repeat the sequence. We had to make sure we used a counter so that this property of the dot matrix display was encountered. In other words, we had to use a counter, taking output from that counter through NOT gates and disable the rows in such a way that the counter had the ability to repeat its count, just like a ring counter, as you can understand if from our syllabus. And that's why I used the Johnson counter. We took output from 8 output pins of Johnson counter, inverted them through NOT gates, and then fed those outputs to 8 rows of our LED dot matrix display. And for operation of this Johnson counter, we needed a clock which was obtained from a 555 timer which operated in stable mode, or in other words, the timer give out pulses continuously. Now we have to control any 4 columns of the dot matrix display. Actually, since we used the bidirectional shift register which could only control 4 bit, or in our cases 4 LED, that is why we took the plan of controlling any 4 columns of this dot matrix display, and then we had to make sure that the columns lit up randomly. How we achieved this task? We achieved this task through linear feedback shift register circuit, which was made up with flip-flops and an XOR gate. At first the flip-flops had to be loaded, and that was done by this DPDT switch, as you saw in our simulation. After loading of the flip-flops, we could XOR the signals of the flip-flop and created a pseudo randomizing of sequences. And after taking 2 outputs from this set of pseudo randomizer, we fed the 2 outputs to a 2 to 4 decoder. And as you can see, the outputs are inverted from the chip. We took 4 outputs and then took all those outputs through 4 NOT gates and then fed to any 4 columns as our wished to any 4 columns of the dot matrix display. Yeah, you may have already guessed, since we used a decoder, any of the columns lit up one at a time. Yes, only one column at a time. Now we have to make sure that the LEDs lit up either from shifting from right to left or left to right. And how we achieve this? To 74191 IC or our bidirectional shift register. We took output from this bidirectional shift register to control our LEDs either left to right shift or right to left shift as the game demanded. And this shifting was controlled by two DPST switches, with the lower DPST controlling the left shift of the LEDs and the upper DPST switch controlling the right shift of the LEDs. Now, through a set of digital logic gates to 2 NAND, 8 NOR gates and 2 OR gates, we counted the logic which was to be implemented to realize the win or loss for this game. As you saw in our simulation, whenever an LED was lit up right under the last lit up row of the dot matrix display, we counted a win. The output from the OR gate, yes, this OR gate counts the wins. The output from the OR gate is fed to an up or down counter, and output from this up or down counter is fed to a BCD to 7 segment decoder circuit, which in turn drop a common anode 7 segment display. This OR gate took hint of the losses, and the output from this 4 input OR was fed to another counter, and as usual output from this counter was fed to BCD 7 segment decoder, and then the red common anode 7 segment display was dropped to display our losses. As you can see, at the very beginning we actually used a common decade counter 7490 to count this either the losses or the wins. Yes, this is loss and this is win. But then we changed the design to take into account a parallel load capability of our game. As you saw in the simulation, if you got bored of the game and then use the DPDT, pushed this DPDT switch, the counters are all reset to 0, and then you are free to go once again in this game. So all in all, this is how we actually implemented the circuit through our logic. Yes, one thing here, as you can see, there are 4 NOT gates here. Output from the last NOT gate is fed to the clock of bidirectional shift register, and the input of this NOT is actually connected through a DPST switch. Why we use this arrangement of 4 NOT gates, although the output would have been same? We actually use this to create a hardware delay in our setup so that the shifting of the LEDs would work properly. We also saw only using 2 NOT gates the whole setup worked perfectly, but for a better result we used 4 NOT gates. All in all, this was how we implemented our logic. Thank you for watching, and next you will see a practical part of while we are working on this project. Thank you.